Okay, so this question says to calculate the mass of oil that experiences an increase in temperature of 25 degrees Celsius when a 0.7 kilogram mass of steel is quenched from 900 degrees Celsius to 80 degrees Celsius. They give us the specific heat capacity of oil as 1.5 kilojoules per kilogram degree Celsius and that of steel as 0.45 kilojoules per kilogram degree Celsius. So we should recognize this as a heat transfer in mixtures question, and in this case the steel will be losing heat. If we are to assume that there are no losses to the atmosphere or to the vessel containing the oil in this case, then the total heat transfer or the net heat transfer, that is the net heat gain or loss, must be zero, which means that the heat that is lost from the steel will be absorbed by the oil and only the oil. So, as is customary with all these questions, we are first to pull out or extract the data, and we are going to do it in this manner. So I'm going to start by writing steel, and I'm going to consider the data for steel. So I have that the mass is, for steel, I'm going to call the mass for steel M1 to facilitate the calculation, make it a little bit easier. Steel M1 as 0.7 kilograms. C1 for steel 0.45 kilojoules per kilogram degree Celsius. The information that we have there for temperatures would be TF 80 degrees Celsius, TI 900 degrees Celsius, and of course we could calculate then delta T in this case for the steel, which is going to be 80 minus 900 degrees Celsius, which leaves us with negative 820 degrees Celsius. And in a similar manner, we'll pull out the information for the oil. Right, so we'd have to calculate the mass in this case. So we say mass is a question mark, and this is what we have to calculate. We'll consider the other data, in this case here C. We'll call this M2 for the mass of the oil. So we could call the specific heat capacity of the oil here as C2. So 1.5 kilojoules per kilogram degree Celsius. Alright, so as far as the temperatures, we will have the final temperature of the oil. In this case, we will not have the initial temperature of the oil, but we know that the temperature change, and in this case that is what is important. The temperature change is 25 degrees Celsius. If we wanted, we could have calculated the initial temperature of the oil, but in this case we'll leave it, and we can just write in the final temperature of the oil. We know that thermal equilibrium will be reached, and as such the final temperature of the oil will be the final temperature of the steel. Now that we have the information, we should come up with an equation that could us to calculate the M. So we are going to start by saying that the net heat that is lost or gained during this heat transfer, because it's a closed system, has to be zero. We assume no losses. Now, what this means is that the heat loss, which is Q, and we can calculate that as MC delta T. In the case of steel, it's going to be M1 C1 delta T. If we add that to the heat that was gained by the oil, that's also then MC delta T, in this case M2 C2 delta T. We'll equate this to 0. Now we could substitute values. So I'll substitute the values for the steel first. 0.7 kilograms multiplied by 0.45 kilogram, in this case kilojoules per kilogram degree Celsius, multiplied by the change in temperature. The steel loses heat, negative 820 degrees Celsius. And we are going to add that to M2C2 delta T. M2 is an unknown, C2, so we'll multiply that by 1.5 kilojoules per kilogram degree Celsius, and finally by delta T. And this all works to 0. Delta T in this case being the 25 degrees Celsius. Right, should work to 0. So I'll pause the video, and when I come back I'll have the values for each of these. Alright, so 0.7 times 0.45 times negative 820 gets me negative 258.3, and the units will be left with, if these cancel, will be the kilojoule. Now we have to add that to M2 multiplied by 1.5 times 25, 37.5, and we could work the units as well. Degree Celsius and per degree Celsius will cancel, and we'll be left with M2 times 37.5 kilojoules per kilogram. And again, this has to work to 0, so we could simplify this. So we could say then that M2 times 37.5 kilojoules per kilogram will be equal to positive 258.3 kilojoules, which means M2 equals 258.3 kilojoules divided by 37.5 kilojoules per kilogram. Alright, so we cancel the units here, kilojoule and per kilojoule, and we'll be left with 1 on the kilogram, which is the kilogram, and numerically this works to 6.89 kilograms. So it looks like a lot of calculation. It isn't too much a calculation, so I'm certain you'll have fun with the others.